Every picture the James Webb Space Telescope has ever taken of deep space is photobombed by them. Tiny, red, everywhere. Hundreds of little crimson dots scattered across the background of nearly every deep field image, in places where nothing was supposed to be. Astronomers stared at them for almost 4 years and had no answer. They appeared in the first billion years after the Big Bang, crammed into spaces smaller than our own solar system, yet burning with the light of 250 billion suns. Gas inside them moves fast enough to travel from Earth to the Moon in seconds. Every theory scientists tried failed. Every detector came back silent. The dots broke the rules so completely that some researchers quietly wondered if our understanding of how the universe forms was just wrong. If you enjoy the journey, hit like and subscribe so you never miss what we uncover next. They finally have an answer, and it changes everything. Prepare yourselves. We begin. The image came back at 3 in the morning. A team of astronomers had been waiting months for the James Webb Space Telescope to send its first real deep field image back to Earth. Deep field means the telescope stares at one tiny patch of black sky. A patch so small you could cover it with a grain of sand held at arm's length, and captures every single thing hiding in the dark. When Hubble did this back in 1995, it revealed thousands of galaxies nobody knew existed. Scientists expected Webb to do the same, just sharper, just deeper. What they got was something else entirely. Scattered across the image, hiding behind the galaxies, between the galaxies, sometimes right in front of them, were hundreds of tiny red dots. No shape, no structure, just small, bright, crimson points of light. They were not supposed to be there. Nothing in any existing model predicted them. The team ran the data again. The dots were still there. They checked for instrument errors. Nothing wrong with the telescope. The dots were real. One researcher later described the moment as seeing footprints in a room you were certain was empty. Word spread fast. Other teams pulled up their own Webb images and found the same thing. Every deep field shot was full of them. Astronomers started calling them little red dots, not a technical name, just what they were. Tiny, red, everywhere. Over 1,000 of them were catalogued in the months that followed, and that number kept climbing. Here is the first thing that made scientists nervous. These dots existed in the very first billion years after the Big Bang. The universe is about 13,800 million years old. These objects formed when it was barely a toddler. Looking deep into space is the same as looking back in time, because light takes time to travel. The light from these dots left its source over 13 billion years ago. What Webb was seeing was not the modern universe. It was the universe in its infancy, and the infancy was full of things that should not have been able to exist yet. The second thing that made scientists nervous was the brightness. The most luminous of these dots were pumping out as much light as 250 billion suns combined from a single point, and that point was tiny, smaller than the distance from our sun to the nearest star, smaller, in some cases, than our own solar system. Something that small, producing that much light, was physically difficult to explain with any normal model. Stars could not do it. Known galaxies could not do it. Whatever was generating that energy was doing something extreme. For the first few months, the leading idea was dense star clusters. Early galaxies so packed with young stars that they blazed like miniature suns all crammed together. It was a reasonable starting point. It turned out to be completely wrong, and the math that dismantled it was brutal. If you tried to pack enough stars into one of these dots to explain the light output, you would need to squeeze billions of suns into a space roughly the size of our solar neighborhood. The gravity alone would tear the whole structure apart in seconds. A star cluster that dense cannot survive. Physics simply does not allow it. So the star theory died quickly, and whatever replaced it was going to have to be something far stranger. Hubble stared at the same patch of sky for over 20 years. It photographed deep space more times than any telescope in history. It gave us some of the most iconic images humans have ever produced. Walls of galaxies stretching back billions of years, ancient light frozen into photographs. Astronomers trusted Hubble so completely that if something was not in a Hubble image, the assumption was simple: it did not exist, or it was too faint to matter. The little red dots were neither. They were in the same sky Hubble had been watching. They were bright enough to matter. Hubble just could not see them. And the reason why tells you something important about how the universe hides its secrets. Light is not just one thing. What we call visible light, the colors you see with your eyes, is only one narrow slice of a much wider range of energy called the electromagnetic spectrum. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays are all the same fundamental phenomenon, just vibrating at different frequencies. Our eyes evolved to detect one small band of that spectrum. Telescopes are built to extend that range. Hubble was designed to see visible light and a small amount of ultraviolet. That sounds like enough until you understand what happens to light over 13 billion years of travel. Space is expanding. Every second, the fabric of the universe is stretching outward in every direction. When light travels through expanding space, the stretching pulls the light waves apart, making them longer. Longer light waves shift toward the red end of the spectrum. Keep stretching those waves for long enough, and visible light becomes infrared light. Infrared sits just below what human eyes can detect, and it sat just below what Hubble was built to capture. The little red dots were not invisible because they were dim. They were invisible to Hubble because their light had been stretched completely out of Hubble's range. 13 billion years of cosmic expansion had redshifted everything they emitted into the infrared, the one band Hubble could not see. Webb was designed from the start to capture infrared light. That was its entire purpose. Engineers built gold-coated mirrors, special detectors, and a massive sun shield the size of a tennis court, just to keep the telescope cold enough to detect faint infrared signals without its own heat drowning them out. The whole machine was engineered around one goal: seeing light that older telescopes were blind to. The moment Webb opened its mirrors and pointed at deep space, the dots appeared everywhere. They had always been there. Hubble had been staring right through them for decades without knowing it. This matters beyond just telescope design. It means our entire picture of the early universe was incomplete. Every model astronomers built about what the first billion years looked like was based on data that was missing a major category of object. The little red dots were not a rare anomaly. They were so common they showed up in the background of almost every image Webb captured. They were part of the furniture of the early universe, and humanity had no idea they existed until 2022. Every answer Webb gave us immediately produced a harder question. If these dots were everywhere, what exactly were they? And why were they only there, in that early period, and nowhere in the modern universe? Something happened to them. Something made them disappear, finding out what took 4 more years. When you look at the night sky, you are not seeing the present. Every single point of light up there is a message from the past. Light travels fast, about 6 trillion miles every year, but the universe is so enormous that even at that speed, light takes serious time to cross it. When you look at the moon, you see it as it was about 1.25 seconds ago. The sun is 8 minutes in the past. The nearest star system is over 4 years old by the time its light reaches your eyes. Now, stretch that out to the scale Webb is working at. The little red dots exist in the first billion years of the universe. The universe is nearly 14 billion years old. That means the light Webb is capturing from these objects left its source over 13 billion years ago. When that light started its journey, Earth did not exist. Our sun did not exist. The Milky Way was still taking shape. The light has been traveling through expanding space for longer than our entire planet has been around. When Webb photographs a little red dot, it is not seeing what that object looks like today. It is seeing a snapshot of something that existed 13 billion years ago, frozen in the moment its light departed. Whatever that object became afterward, whatever happened to it over the following billions of years, is invisible to us. We only see it as it was in its very first moments. This is why astronomers got so alarmed. The early universe was supposed to be simple. Right after the Big Bang, matter was mostly hydrogen and helium gas, spread fairly evenly across space. Gravity slowly pulled that gas together into the first stars, which were massive and short-lived and exploded. Those explosions created heavier elements. Those elements eventually built planets. Galaxies formed gradually as gravity herded billions of stars together over enormous spans of time. The whole process was supposed to be slow, orderly, predictable. The little red dots broke that picture immediately. Objects that bright, that compact, that powerful should have taken billions of years to build up. They needed time to gather mass, to merge, to grow. But there they were, fully formed and blazing, less than 1 billion years after the Big Bang. The timeline made no sense. It was like finding a fully built skyscraper in a field where the concrete was poured yesterday. One comparison that helps: imagine the universe as a human life. 14 billion years equals a full lifespan of about 80 years. The first billion years would be roughly the first 6 years of life, kindergarten age. The little red dots were forming in that kindergarten phase. Structures that complex and powerful have no business existing in kindergarten. Scientists use the word redshift to describe how far back in time an object sits. The higher the redshift, the older the light, the further back in time you are seeing. The little red dots have some of the highest redshifts ever recorded. They sit at the very edge of what we can observe, at the boundary of the knowable universe. And they were there, blazing, before anything like them was supposed to exist. The question was no longer just what they were. The question became how they got there so fast. Science works by building the best possible explanation from available evidence, then testing it until it breaks. The first serious explanation for the little red dots broke fast. When astronomers looked at the data in late 2022 and early 2023, the most logical starting point was compact star clusters. Early galaxies packed so tight with newborn stars that their combined light blazed like a single point. This made sense on the surface. The early universe was full of young, hot, massive stars. Those stars burn incredibly bright. Pack enough of them close together and you might get something small and intensely luminous. Teams ran the calculations. They figured out how many stars you would need to produce the observed brightness. Then they calculated how much space those stars would require, even at the tightest physically possible packing. Then they compared that space to the observed size of the dots. The numbers did not come close to working. The brightest dots shine with the light of 250 billion suns. Our entire Milky Way galaxy contains roughly 250 billion stars, and it stretches about 100,000 light-years across. These dots were producing equivalent light output from a space smaller than 3/10 of a light-year. Our solar system alone is about 2 light-years wide, from edge to edge if you include the outer cloud of icy debris orbiting the Sunday. The dots were smaller than that. To pack enough stars into that space to explain the brightness, you would need a density that physics actively forbids. Stars that close together exert gravitational forces on each other so strong that the whole cluster would collapse inward almost instantly. The stars would smash into each other, merge, explode, and tear the structure apart. A star cluster of that density and brightness could not survive for more than a few thousand years. The dots had clearly been around much longer than that. There was another problem. Stars produce a specific pattern of light. When you spread starlight out across wavelengths, it creates a signature that astronomers can read like a fingerprint. The little red dots did not match the stellar fingerprint. Their light spectrum looked different in ways that pure starlight could not explain. Something else was generating energy inside them. The star cluster theory was officially set aside by mid-2023. What replaced it was a much darker concept. If stars could not explain the light, and if the energy source was more powerful than any collection of stars could produce, then the only remaining candidate was something that does not burn fuel the way stars do. Something that generates energy not through nuclear fire, but through gravity so extreme that matter itself gets torn apart at the edge of an abyss. A black hole, but not just any black hole. To produce that much light from that smaller space, the black hole would have to be enormous. Millions of times the mass of our sun, actively feeding, swallowing gas and dust, at a rate that would make it one of the most violent objects in the early universe. That answer solved one problem and immediately created three more, because black holes of that size should not exist in the first billion years. And black holes that are actively feeding should be screaming across the entire electromagnetic spectrum. These dots were completely silent. Stand outside on a clear night and hold up your fist at arm's length. The patch of sky your fist covers contains thousands of galaxies. Each galaxy holds hundreds of billions of stars. The light from all of those stars, all of those galaxies, barely makes a dent in what your eyes can detect. Space is mostly dark. Now, imagine cramming the light of 250 billion suns into a dot smaller than your fist from that same distance. Smaller than our solar system in actual size. That is what the brightest little red dots are doing. The sheer energy output is almost impossible to put into context, but here is one way to try. Our sun is a middle-aged, medium-sized star that produces enough energy every second to power all of human civilization for about 500,000 years. The most luminous little red dots produce the equivalent of 250 billion suns, all at once, continuously, from something smaller than the distance between our sun and its nearest stellar neighbor. For the math to even approach working, whatever is inside these dots has to convert matter into energy with extreme efficiency. Nuclear fusion in stars, the process that makes them shine, converts less than 1% of the available mass into energy. The process happening near a feeding black hole, where gas spirals into an incredibly hot disk before crossing the point of no return, can convert up to 40% of the incoming mass into pure energy. Black holes are the most efficient engines in the known universe. That efficiency is the only way to explain what the dots are doing. But here is where the first major puzzle appeared. When astronomers measured the actual size of the light-emitting region inside the brightest dots, they found it was less than 3/10 of a light-year across. 1 light-year is about 6 trillion miles. 3/10 of a light-year is roughly 1.8 trillion miles, which sounds enormous until you realize that the distance from our sun to the very next star is about 4 light-years. The source of all that light was crammed into less than 1/10 of the gap between our star and its nearest neighbor. That level of compactness only makes sense for one kind of object. The energy has to come from something with mass so concentrated that gravity near its surface is essentially infinite. A black hole, surrounded by a superheated disk of infalling gas, releasing energy at a rate that dwarfs every star in our galaxy combined. The size of the black hole hiding inside the dots had to be somewhere between 100,000 and 10 million times the mass of our Sunday. Astronomers call objects in that range supermassive black holes. The one sitting at the center of our own Milky Way is about 4 million solar masses. The black holes inside the little red dots were potentially in the same weight class or heavier, and they existed when the universe was a fraction of its current age. Here is what made everyone stop breathing. Building a black hole that massive normally takes billions of years of slow growth. Swallowing gas, merging with smaller black holes, repeating the process across cosmic timescales. The little red dots suggested this was happening in a tiny fraction of that time. Something was feeding them faster than physics said was possible, and they were hiding it perfectly. Every black hole that astronomers have ever confirmed was found the same way. Noise. Black holes announce themselves. When gas falls toward a black hole, it does not drop straight in like a rock down a well. It spirals inward, forming a flat disk that spins faster and faster as it gets closer to the center. The friction in that disk heats the gas to temperatures of millions of degrees. At that temperature, matter screams. It blasts out X-rays, radio waves, and ultraviolet radiation in all directions. The region around an actively feeding black hole is one of the loudest places in the universe in terms of radiation. Astronomers found most of the supermassive black holes in the modern universe by listening for that noise. Radio telescopes, X-ray satellites, ultraviolet detectors, all of them built to catch the signal of a feeding black hole. It works. We have confirmed thousands of them this way. The little red dots made no sound at all. No X-rays, no radio waves, no ultraviolet blasts. Just the red glow of heated gas, soft and relatively quiet by cosmic standards. Every detector designed to catch a feeding black hole came back empty when pointed at the dots. If the standard detection methods were the only tools available, astronomers would have concluded there was no black hole there at all. But the energy output demanded one. The size demanded one. The only object that could produce that much light from that smaller space was a feeding supermassive black hole. So where was the noise? The answer came slowly, built from years of combined observations. The black holes inside the little red dots are buried. Buried so deeply inside incredibly thick clouds of ionized gas that the radiation cannot escape. The gas surrounding these objects is not like a thin atmosphere. It is a dense, churning shell that absorbs the violent X-rays and radio waves before they can travel outward. The cocoon traps the energy. The outer layer of heated gas glows red from the absorbed heat, and that glow is all we see. Ionized gas is gas where the atoms have had electrons stripped away by intense energy, making the gas electrically charged and highly reactive. Near a feeding black hole, the radiation is so intense that the surrounding gas stays ionized, charged, and dense, and almost impenetrable. The cocoon acts like a perfect sound-dampening wall around the most violent event in the early universe. Picture the loudest concert you have ever imagined. Now seal it inside a room with walls 100 feet thick, packed with material that absorbs every frequency of sound. From outside, you hear almost nothing. That is what the little red dots are doing, except instead of sound, the walls are absorbing radiation, and the concert inside is a supermassive black hole consuming matter at a ferocious rate. The disguise is so complete that these objects fooled every detection method available for decades. Hubble missed them entirely. Radio telescopes heard nothing. X-ray satellites returned blank data, and there were 1,000 of them in the background of every image, hiding in plain sight. The cocoon was the key. But understanding how it stayed intact without being blown apart by the black hole inside, it was about to become the next major problem. To understand why the silence of the little red dots was so alarming, you need to understand what a normal feeding black hole actually sounds like to our instruments. Quasars are the gold standard. A quasar is a supermassive black hole actively eating enormous amounts of gas, and it is the brightest sustained object in the known universe. The most powerful quasars outshine their entire host galaxies by a factor of 1,000. They fire jets of superheated plasma thousands of light years into space at nearly the speed of light. They flood the universe around them with X-rays, radio waves, and visible light so intense that astronomers can see them from the opposite end of the observable universe. When astronomers discovered quasars in the 1960s, the signal was so overwhelming that they initially thought they were looking at nearby stars. The light was that strong. It took years of careful analysis to realize quasars were sitting billions of light years away and were among the most distant objects ever observed. The little red dots should be quasars. Based purely on their energy output, based purely on the mass of the black holes estimated inside them, they should be blasting signals in every wavelength visible from across the universe. Any instrument designed to detect active black holes should have flagged them immediately. Instead, nothing. X-ray observatories pointed at the dots, returned no significant signal. Radio telescopes found silence. Ultraviolet detectors registered nothing unusual. The dots seemed to emit only in infrared, only that soft red glow, as if someone had installed a filter between us and whatever was happening inside. Scientists use a technical term for this: obscured. An obscured active black hole is one where the surrounding material blocks the radiation before it reaches us. Astronomers have known about obscured black holes for decades. They are common in the modern universe. Dust and gas clouds around the feeding region absorb the outgoing radiation and re-emit it as gentler infrared light. But the level of obscuration in the little red dots appeared to be far beyond anything seen in modern active black holes. The cocoon around them was not a thin dust cloud. It had to be dense enough to absorb almost the entire output of a feeding supermassive black hole, which is one of the most energetically extreme events in nature. Here is what made this deeply strange. In the modern universe, when a black hole feeds aggressively, it eventually blows away its own surrounding gas with radiation pressure. The intense outpouring of energy pushes the gas outward, clears the area around the black hole, and the quasar becomes visible. This process, called feedback, is thought to regulate how big black holes can get and how fast they can grow. The little red dots seem to be skipping this step entirely. The cocoon was staying intact, the black hole was feeding, generating enormous energy, and the surrounding gas was somehow absorbing all of it without being blown away. Either the cocoons were far thicker and denser than anything in the modern universe, or the black holes inside them were feeding in a way that produced less outward pressure than expected. Either option required explaining something new about how black holes behave in the early universe. And underneath all of this was a deeper question nobody had answered yet. Where did the radio waves actually go? The color of the little red dots is not a coincidence. It is not because the objects are physically red, like a red dwarf star or a glowing ember. The color is something the universe imposed on the light as it traveled across 13 billion years of expanding space. Understanding this explains not just the dots, but something fundamental about the nature of reality itself. Space is expanding. This is one of the most confirmed facts in all of science. In 1929, astronomer Edwin Hubble discovered that galaxies are moving away from us in every direction, and the further away they are, the faster they are receding. This is not because there was an explosion that threw everything outward. The space between objects is literally stretching, like dots drawn on a balloon as you inflate it. Every dot moves away from every other dot, and the ones furthest apart move the fastest relative to each other. Now think about what happens to a light wave traveling through that stretching space. A light wave has a specific length between its peaks, called its wavelength. Blue light has a short wavelength. Red light has a longer one. Infrared light has an even longer wavelength. When a light wave travels through space that is actively stretching, the stretching pulls the wave apart. The wavelength gets longer. As the wavelength increases, the light shifts toward the red end of the spectrum, and then past it, into the infrared, which is invisible to human eyes. Astronomers call this cosmological redshift. The further light has to travel, the more the universe stretches it. Light from a galaxy 1 billion light-years away is redshifted a little. Light from a galaxy 10 billion light-years away is redshifted a lot. Light from the little red dots, which traveled over 13 billion light-years, has been stretched so dramatically that what was originally ultraviolet or visible light has been pulled all the way into the infrared band. By the time that light reaches us, it carries the red glow of its long journey. This is also why Webb was the only telescope capable of detecting them in large numbers. Hubble's detectors were designed primarily for visible and ultraviolet light. The deeply redshifted infrared light from the distant early universe simply passed through Hubble without registering. Webb's detectors were specifically engineered to capture infrared, making it the first instrument sensitive enough to catch the stretched light of objects from the universe's first billion years in such detail. There is something almost philosophical about this. The little red dots are not showing us what they look like. They are showing us the echo of a journey. Every photon of light arriving from these objects has been traveling since before our planet existed, stretched and distorted by the expansion of space itself, arriving billions of years later as a faint infrared whisper. The red color is, in a sense, the signature of time. Measure that color precisely, and you can calculate exactly how far the light traveled and how long ago it left its source. The redness is a timestamp baked into the light by the universe itself, and reading that timestamp told astronomers something extraordinary. These objects were not scattered evenly across cosmic history. They existed specifically in one narrow window of time, the first billion years, and then they seemed to vanish. Why they vanished was one of the hardest questions anyone had ever asked about the early universe. The James Webb Space Telescope did not happen quickly. The idea for a successor to Hubble began circulating in the mid-1990s. The actual planning and design process started around 1996. It took over 25 years of engineering, funding battles, redesigns, delays, and one terrifying launch on Christmas Day 2021 before Webb finally reached its operational position in space. 25 years. The scientists who first proposed it were approaching retirement by the time it worked. The reason it took so long is that building a telescope to see infrared light from the edge of the observable universe requires solving a physics problem that has no easy solution. Infrared is essentially heat radiation. Every warm object emits it, including telescopes, their electronics, and the humans who build them. To detect the faint infrared glow of objects 13 billion light-years away, the telescope itself has to be colder than the signal it is trying to receive. Webb operates at about -449 degrees Fahrenheit. That is less than 10 degrees above absolute zero, the coldest temperature that can theoretically exist. To reach that temperature in space, Webb carries a massive 5-layer sunshield roughly the size of a tennis court. Each layer reflects and radiates away heat from the sun, Earth, and Moon. The telescope on the shadow side gets cold enough to see what it needs to see. The mirrors themselves were another engineering problem. Webb's primary mirror is about 21 feet across, which is too large to fit inside any rocket ever built. Engineers solved this by making the mirror fold up like origami. 18 hexagonal gold-coated segments click into position after launch, aligning themselves with precision measured in nanometers, which are units smaller than a single wavelength of visible light. Gold coating is not decorative. Gold reflects infrared light better than almost any other material, and at Webb's operating temperatures, it stays stable without degrading. The telescope launched, unfolded perfectly, and reached its operating position about 1 million miles from Earth, far enough that Earth's own heat could not interfere with its observations. The first full-color images were released in July 2022. Within weeks, the little red dots started showing up. Researchers were not specifically looking for them. They appeared in the background of images taken for other purposes, faint red points crowding the distant background of the universe. The discovery was partly accidental, made possible only because Webb was capturing so much more of the infrared sky than any previous instrument. This raises a humbling point. The little red dots had been there the entire time. They existed throughout all of human history, their ancient light passing through the solar system, passing through Earth's atmosphere, invisible to every instrument ever built. Galileo stared at the night sky and had no idea they were there. Hubble photographed the same patches of sky and captured nothing. Every astronomer who ever lived was looking right past them. It took one specific telescope, built by thousands of people over 25 years, operating at near absolute zero, 1 million miles from Earth, to finally catch their light, and even then, nobody knew what they were. For almost 4 years, the little red dots stayed quiet, over 1,000 of them catalogued. Teams of astronomers studying them from every angle, theories proposed and challenged and revised. But no X-ray signal, no radio emission, nothing from any detector except that soft infrared glow. The black hole model had become the leading explanation, but without direct confirmation, some researchers held on to alternative ideas. Maybe the dots were something entirely new. Maybe the black hole theory was wrong. Then, in April 2026, a single dot changed everything. NASA announced that researchers had combined data from two telescopes simultaneously, the James Webb Space Telescope and the Chandra X-ray Observatory. Chandra is a space-based X-ray telescope that has been operating since 1999. It detects high-energy X-ray radiation from extreme cosmic events, the kind of radiation that feeding black holes produce. Chandra and Webb had been pointed at the same region of the sky at the same time, and one specific object had appeared in both datasets. The object sits 11,800,000,000 light-years away. Its official catalog number is long and forgettable. What matters is what it did. It emitted a faint but unmistakable X-ray signal, the first X-ray signal ever detected from a little red dot. Faint is the key word. The X-ray emission was far weaker than you would expect from a fully exposed feeding black hole. If this were a standard quasar, the X-ray output would be blinding. This signal was a whisper, but it was there, and it was real, and it pointed directly at what was happening inside the dot. Astronomers described what they were seeing as a transition phase. The thick gas cocoon surrounding the black hole was not completely intact anymore. Patchy holes had opened up in the cloud. As the black hole consumed the surrounding gas, it was slowly eating through its own disguise. Gaps were forming in the shell, and through those gaps, X-ray radiation was leaking out for the first time. Picture a sealed vault that has been locked for billions of years, and one day a small crack appears in the wall. You cannot see inside clearly, but through the crack you can confirm something enormous is in there. That crack is what Chandra detected. The implications were significant. This single object bridged the gap between the mysterious silent dots and the loud, detectable quasars that astronomers see in the modern universe. It suggested a sequence. A little red dot is a young, buried, feeding black hole. Over time, it consumes its cocoon. The shell grows thinner and patchier. Radiation leaks out in increasing amounts. Eventually, the cocoon is gone, and the black hole stands fully exposed as a blazing quasar. The little red dots might be the childhood phase of the largest black holes in the universe. And if that is true, the supermassive black holes sitting at the center of every modern galaxy, including the Milky Way, may have once looked exactly like a tiny, quiet, red dot hiding in the background of the universe. The silence was finally broken. But the biggest questions were still waiting. The cracking cocoon was not just a poetic image. It was a sequence of events that, once understood, explained one of the longest-standing mysteries in black hole science. Modern galaxies almost all have supermassive black holes at their centers. That fact is confirmed. What is not fully understood is how those black holes got there. The standard model says they grew slowly over billions of years, feeding on surrounding gas, occasionally merging with other black holes when galaxies collided. It is a gradual, patient process that fits neatly into the timeline of the universe after the first billion years. The little red dots do not fit that timeline at all. They suggest something faster, something more chaotic, happened in the early universe. And the transition phase observed in the X-ray emitting dot gave scientists the first real glimpse of that process in action. Here is what the transition likely looks like, step by step. In the very early universe, massive clouds of primordial gas, mostly hydrogen, collapse under gravity and begin feeding a newborn black hole directly. The black hole grows rapidly, far faster than the standard model predicts, because it has access to an enormous, dense supply of gas pouring in from all directions. As the black hole feeds, it heats the surrounding gas. The heating ionizes the gas, creating the thick, electrically charged cocoon that traps the outgoing radiation. For a while, the cocoon holds. The black hole eats. The gas absorbs the energy. The system is in a kind of violent equilibrium where the input of matter and the output of energy are roughly balanced. From the outside, we see a little red dot, bright, compact, and silent. But the equilibrium cannot last forever. As the black hole consumes gas from the inner edge of the cocoon gets thinner in spots. Turbulence in the gas creates uneven densities, and in the thinner regions, radiation begins to push through. A hole forms. Then another. The X-ray signal leaks out in pulses, faint and irregular, exactly matching what Chandra detected. As the holes grow, the radiation pressure from the exposed black hole begins accelerating the remaining gas outward. The cocoon is not just thinning, it is being actively blown away. This is the same feedback process that operates in modern quasars. But in the early universe, it appears to have started from inside a far denser and more chaotic environment. Once the cocoon is fully dispersed, the black hole stands exposed. It is now a visible, active quasar, identifiable by every detection method available. The little red dot phase is over. The object has graduated into something recognizable. This transition probably takes millions to hundreds of millions of years. On a human timescale, that is forever. On a cosmic timescale, it is remarkably fast. What the cracking cocoon tells us is that the early universe was not just forming black holes, it was forming them in a specific way, hidden, fast, and deeply buried, before eventually revealing them to the cosmos. The early universe had a habit of keeping its most violent secrets locked away, and we are only now finding the keys. In 2008, a theoretical physicist named Mitchell Bagelman published a paper that most of the astronomy community filed under interesting, but probably not real. The paper described a type of object called a quasistar, though it has also been called a black hole star. The idea was this: in the very early universe, before there were any heavy elements, massive clouds of pure hydrogen and helium could collapse under their own gravity. In modern astrophysics, collapsing gas clouds form stars, and stars eventually live out their lives, and some of them produce black holes. But Begelman's model proposed a different path. If the cloud was massive enough and dense enough, the center of the collapsing gas could form a black hole directly, before a stable star ever had the chance to ignite. The black hole would then sit at the heart of the still collapsing gas cloud, feeding on it from inside. As the black hole fed and grew, the energy it released would push outward against the surrounding gas, inflating a massive glowing envelope around itself. From the outside, this object would look like an enormous, very bright star. It would glow, it would have a defined outer edge, but at its core, instead of nuclear fusion, there would be a feeding black hole, using gravity rather than atomic fire to generate its energy. The structure would be inherently unstable. Eventually, the black hole would grow large enough that the gas envelope could no longer contain it. The whole system would collapse or disperse, leaving behind a massive black hole with a head start on growth that no normal stellar evolution could match. When Begelman published this, it was a theoretical curiosity. There was no observation of any object that might fit the model. The physics was interesting but untestable. Most astronomers moved on. Then the little red dots arrived. Some of the characteristics of the dots matched the black hole star model in striking ways. The compactness of the light source, the enormous energy output without the X-ray screaming of a typical quasar, the thick surrounding gas that absorbs radiation, the fact that these objects seem to behave like neither a normal galaxy nor a normal quasar, but something between. If even a portion of the little red dots are black hole stars, it would mean Begelman's paper was describing a real class of object that exists in nature, something theoretical physicists imagined 17 years before astronomers finally had a telescope capable of seeing them. This remains an active debate. The majority view is that the dots are standard black holes buried in dense gas, and that model explains most of the data. But the black hole star theory is not dismissed. For a subset of the dots, particularly the most extreme ones, the black hole star explanation fits the observations in ways that the standard buried black hole model struggles to match. Science does not always give clean answers. Sometimes two different explanations can both be partially true, applying to different members of the same population. What makes this specific theory remarkable is not just that it might be right, it is that someone thought to imagine this object at all. decades before anyone had seen anything like it. In the standard story of how the universe produces black holes, the path runs through stars. A star forms. It burns for millions or billions of years. When the fuel runs out, the most massive stars collapse inward, their cores crushed to densities beyond anything in normal matter, producing a black hole. The black hole then grows by consuming surrounding gas and dust, and occasionally by merging with other black holes over billions of years. This path is well understood. Astronomers have confirmed it through multiple lines of evidence. It is how the black holes in the modern universe formed. The process takes time. It requires stars to be born first, to live, and to die. Only then do black holes appear. The little red dots suggest the universe had a shortcut. The shortcut is called direct collapse, and it describes a situation where a massive cloud of gas does not pass through the star phase at all. Under specific conditions that existed in the early universe, a cloud can bypass stellar ignition entirely and collapse straight into a black hole. No star forms. No supernova explodes. A black hole simply emerges from the gas, already large, already hungry. The conditions required for direct collapse are demanding. The gas cloud must be enormous. The temperature has to stay high enough to prevent the cloud from fragmenting into smaller clumps that would each form individual stars. Nearby ultraviolet radiation from other early stars can provide this heat, keeping the gas as one coherent mass rather than breaking it into pieces. When the conditions align, gravity wins without opposition. The cloud falls inward. The center reaches a density where no known force can stop the collapse. A black hole forms directly, with a starting mass potentially hundreds of thousands of times greater than our Sunday. This starting mass is crucial. A black hole that begins with a massive head start does not need billions of years to become supermassive. It can reach the required size in a fraction of the time, feeding continuously from the dense, gas-rich environment of the early universe, where matter was far more concentrated than it is today. The early universe was different in ways that made direct collapse easier. The cosmic environment in the first billion years had higher densities, stronger gravitational concentrations, and specific patterns of ultraviolet radiation from the first generation of stars, all conditions that modern astrophysics says are not present anymore. Direct collapse black holes, if real, would explain why the little red dots look so different from anything in the modern universe. They formed through a path that no longer exists. The raw material and the environmental conditions that allowed them to form are gone, consumed and dispersed as the universe aged and expanded. This also explains their disappearance. The little red dots exist only in that narrow window of time, because the process that created them only worked during that specific era. Once the universe expanded and diluted, and the dense primordial gas clouds were used up, the factory shut down. The dots are the last artifacts of a cosmic process that will never happen again. Every science class teaches the same rough version of how the universe evolved. Big Bang, rapid expansion, cooling, the first hydrogen forms. Gravity pulls that hydrogen into clumps. Clumps become stars. Stars live and die. Some produce black holes. Small black holes grow slowly. Galaxies form around them. Over billions of years, galaxies merge, and the black holes at their centers grow larger through mergers and feeding. It is a satisfying sequence. Every step follows logically from the one before, and for the middle and late universe, it matches observations extremely well. The little red dots do not match. The core problem is time. A black hole that begins as a collapsed stellar remnant starts with a mass roughly equal to a few suns. To grow from that starting point to 1 million or 10 million solar masses, which is the estimated range for the black holes inside the dots, through standard feeding processes alone requires enormous time. Astronomers calculate the maximum rate at which a black hole can feed, a rate limited by the radiation pressure it generates on infalling gas. This limit is called the Eddington limit. At maximum feeding, growing from a stellar remnant to 10 million solar masses takes over 1 billion years under ideal conditions. The little red dots are sitting in the universe's first billion years. They already have masses of millions of solar masses. If they started from stellar remnants, they would need to have been feeding at maximum rate continuously from the very first moments of the universe, with no interruptions. That is not how it works. Feeding is chaotic. Gas supplies run out. Mergers disrupt accretion disks. In practice, black holes feed at well below the Eddington limit most of the time, so the numbers do not add up at all. There are three possible explanations, and astronomers are still fighting over which one is right. The first is that these black holes started with much larger seeds. Direct collapse, as described in the previous chapter, could produce a starting mass of hundreds of thousands of solar masses. With that head start, reaching supermassive scale in the available time becomes at least theoretically possible. The second is that these black holes fed at rates above the standard Eddington limit. Some theoretical models allow for super Eddington accretion under specific conditions, particularly in the dense gas environments of the early universe. If a black hole can exceed the standard feeding cap, even briefly, the growth rate accelerates dramatically. The third is that the masses of the dots have been overestimated. The methods used to measure black hole masses in the early universe are indirect and carry significant uncertainty. If the true masses are lower than current estimates suggest, the timeline becomes less impossible. The honest answer is that researchers do not know which explanation is correct. Possibly, it is a combination of all three. What is certain is that the standard model of black hole growth, the one taught in every textbook, cannot explain what Webb is seeing in the early universe without significant modification. The timeline is broken, and fixing it will require rewriting the rules. Imagine a snowball rolling down a hill. The bigger it gets, the more snow it can pick up, and the faster it grows. A small snowball picks up a little. A larger one sweeps up much more with each rotation. The growth accelerates as the size increases. Black holes grow somewhat like this. A larger black hole has stronger gravity, can pull in more gas from a wider area, and grows faster than a smaller one. The technical term is runaway accretion. As the black hole grows, its gravitational reach expands, feeding more gas toward it, which makes it grow even larger. The problem is that this process has a built-in speed limit. As gas falls toward a black hole, it releases energy. That energy, in the form of radiation, pushes outward. At a certain feeding rate, the outward push of the released radiation becomes strong enough to slow down or stop the inflow of new gas. This is the Eddington limit, the point where the radiation pressure from a feeding black hole begins to fight against its own growth. The Eddington limit depends on the mass of the black hole. A more massive black hole can feed faster before hitting its limit, but the limit scales with mass, which means the growth rate is capped at a fixed ratio regardless of size. At the Eddington limit, a black hole can roughly double its mass every few 100 million years. That sounds fast until you realize how much mass the little red dots needed to accumulate in less than 1 billion years. Starting from a stellar remnant of a few solar masses and reaching 10 million solar masses in less than 1 billion years would require doubling the mass roughly 23 times in a row. At the Eddington limit, that would take about 2 billion years under perfect conditions with no interruptions. The universe was less than 1 billion years old. The only way to close this gap without abandoning known physics entirely is to change one or more of the starting conditions. Either the seeds are larger, meaning direct collapse, produced massive black holes from the start, or the feeding rate exceeded the standard Eddington limit through some mechanism specific to the dense early universe, or the masses are measured incorrectly and the real numbers are smaller than current estimates. Researchers are actively testing all three, and they are not mutually exclusive. A combination of a larger initial seed and periodic super Eddington feeding bursts could plausibly explain what Webb is observing, without requiring any new physics beyond what is theoretically allowed. But the uncomfortable truth is that nothing in the confirmed observational record of modern black hole growth prepared astronomers for what they found in the early universe. The growth rate is simply too fast, and the explanation for it remains one of the most urgent open questions in astrophysics. Something fed these black holes faster than anything in the universe today could manage. The next chapter is about the fuel source, and it is something stranger than most people expect. In the modern universe, a galaxy, like the Milky Way, has a relatively stable gas supply. Gas clouds drift through the galactic disk. Stars occasionally explode and eject material. Gas falls in gradually from the sparse intergalactic medium surrounding the galaxy. It is a slow, intermittent process. Black holes at the centers of modern galaxies feed from this trickle and grow accordingly, which is why modern supermassive black holes are not actively feeding at dramatic rates most of the time. The early universe was completely different. In the first billion years, the universe was far more compact. Matter had not yet spread out into the vast cosmic web of filaments and voids that characterizes the modern large-scale structure of the universe. Instead, matter was concentrated in dense streams and knots, with gas flowing along gravitational channels that connected the early structures to each other. Astronomers call these cosmic filaments, and they act like rivers, funneling enormous quantities of gas toward the gravitational centers of early galaxies and the black holes forming within them. Picture a city in the middle of a flood. Water is not just falling from above, it is rushing in from every direction, along every road, every valley, every low point. The city center receives far more water than it would in any normal rainfall. That is what the early black holes were experiencing, not just local gas supplies, but massive streams of primordial hydrogen and helium flowing toward them from the wider cosmic structure. These streams could explain the super Eddington feeding bursts that some theorists propose. When a dense filament of gas connects directly to a black hole, the inflow rate can temporarily exceed the normal limits because the gas is coming in faster than the radiation can push back against it. The black hole effectively drowns in fuel. There is a geometric component to this as well. Gas falling in from multiple directions along filaments can form a feeding disk that is thicker and more disordered than the thin, clean accretion disks seen in modern quasars. A thicker disk allows more mass to flow inward before the radiation can escape outward and apply the brakes. This model fits with what the little red dots look like. The gas surrounding them appears turbulent and chaotic, based on the velocity measurements of gas orbiting at around 670,000 miles per hour. That is not orderly rotation. That is a system being fed from multiple directions at once, churning and irregular. The cosmic filaments that enabled this kind of feeding were a product of the specific density and temperature conditions of the early universe. As the universe expanded, those filaments thinned out. The rivers slowed. The flood era ended. Black holes in the modern universe receive a trickle compared to what these early monsters were drinking. And that difference in supply is a significant part of why black holes in the early universe grew so fast and why we cannot reproduce those conditions today. The feeding era is over, but it left behind descendants. Most of the little red dots fit within the range of extreme but explainable. Then there is the one they nicknamed the cliff. Discovered in July 2024, the cliff broke records that scientists had not expected to see broken. Even among the little red dots, which are already the most compact, most luminous, most puzzling objects from the early universe, the cliff stood apart. Its light output, its compactness, and the speed of the gas orbiting inside it put it in a category that pushed against every theoretical limit available. The gas inside the cliff moves at speeds approaching 670,000 miles per hour. To put that in perspective, a commercial airplane travels about 500 miles per hour. A rocket leaving Earth's atmosphere travels about 17,000 miles per hour. The gas inside this object is moving roughly 40 times faster than that, continuously, in tight orbits around whatever is at the center. Gas moving at that speed means the gravitational field pulling on it is extreme. The faster the gas moves in orbit, the stronger the gravity has to be to keep it from flying outward. The gravitational force required to hold gas in orbit at that velocity points to a central mass that is on the upper end of the already enormous range estimated for the little red dots. The cliff appeared so extreme that it challenged even the direct collapse and Super Eddington feeding models. If those models were already straining to explain the growth of the average little red dot, the cliff required something even more aggressive. Either the seed mass was larger than any direct collapse model currently produces, or the feeding rate was higher than even the most generous theoretical estimates allowed, or some combination of factors concentrated growth in this one object to a degree that has no parallel in any confirmed observation. Some researchers propose that the cliff might represent a rare extreme case, an outlier even within the population of little red dots, produced by a particularly perfect alignment of conditions, a massive direct collapse seed sitting at the junction of multiple cosmic filaments, feeding continuously without the typical disruptions that interrupt black hole growth. Others argued the cliff was pointing at something more fundamental. If standard physics, even when stretched to its limits, cannot explain a single object, that object might be signaling that the standard physics is incomplete. The cliff has not resolved that debate. It remains the most extreme data point in the little red dot population, the object that forces theorists to push their models hardest and still sometimes come up short. What makes it significant beyond its own strangeness is what it represents as a data point. Science advances fastest at the edges of what can be explained. Every time a theory produces a number and reality produces a bigger one, the gap between them is where new understanding grows. The cliff is that gap made visible, and whatever is sitting at the center of it has been growing, hidden, and silent since the universe was barely old enough to have stars. Nobody has ever seen inside a little red dot directly. The cocoon blocks the view. The dense, churning shell of ionized gas surrounding the central black hole is opaque to most forms of radiation, which is the entire reason these objects stayed hidden for so long. But astronomers can measure what is happening inside the cocoon indirectly by studying the light that does escape and working backward from the physics of how gas behaves under extreme conditions. What they have reconstructed is a portrait of one of the most violent environments in the known universe. The gas inside the cocoon is not sitting still, it is moving, fast. Measurements of the light spectrum coming from the dots reveal a signature called broadened emission lines. When gas moves rapidly toward or away from us, the light it emits gets shifted in frequency, compressed on one side and stretched on the other. The broader and more smeared that emission line appears, the faster the gas is moving. For the little red dots, those lines are extremely broad. The calculation from those measurements gives a gas velocity of around 670,000 miles per hour. That number needs a comparison to land properly. The Earth orbits the Sun at about 67,000 miles per hour, which already feels impossibly fast from a human perspective. The gas inside these cocoons is moving 10 times faster than that, continuously, in all directions, churning like the inside of the most violent storm imaginable, except the storm is larger than our entire solar system and powered by a feeding black hole. At those speeds, the gas is not gently drifting. It is colliding with itself constantly. Those collisions generate heat. The heat further ionizes the gas, stripping more electrons from atoms and keeping the cocoon in a perpetual state of charged, reactive turbulence. The cocoon sustains itself partly through the energy of its own internal violence. Here is the detail that should stop you for a moment. Gas moving at 670,000 miles per hour could travel from Earth to the Moon in less than a second. The Moon is about 240,000 miles away. The gas inside these objects crosses that distance in roughly 1.3 seconds, constantly, everywhere inside the cocoon, in every direction. And this environment, this extreme, seething, billion-degree chaos, is what the black hole is eating. The gas does not fall in smoothly. It swirls, it clumps, dense pockets form and get drawn inward faster than surrounding material. Turbulent eddies, the size of solar systems, spin inside the cocoon. The whole structure is dynamic and changing on timescales that, while slow by human standards, are rapid by cosmic ones. What the cocoon also does is act as a pressure valve. The radiation pouring outward from the feeding black hole at the center pushes against the cocoon from the inside. The cocoon pushes back with its own weight and density. This balance between outward radiation pressure and inward gravitational pressure is what keeps the system in its unusual equilibrium, blazing with energy but sealed to the outside universe. When the balance tips, the cocoon begins to crack, and what happens when it fully breaks open is a transformation that takes the universe from hiding its most violent objects to displaying them for all of cosmic history to see. But before that moment arrives, the interior of a little red dot remains the most sealed, most extreme, and most violent environment produced by the early universe. For most of their catalogued history, the little red dots looked like a single category of object: compact, bright, red, silent. The population of over 1,000 objects seemed to share the same basic profile, which encouraged astronomers to treat them as variations on a single theme: a buried supermassive black hole in a dense gas cocoon. Then someone ran an ultraviolet test and split the category in half. Ultraviolet light sits just above visible light in the electromagnetic spectrum, with shorter wavelengths and higher energy than anything the human eye can detect. It penetrates some types of gas more easily than infrared and interacts differently with various types of matter. When astronomers looked at the little red dots through ultraviolet sensitive instruments, a striking pattern emerged. About 70% of the dots looked the same as in infrared: compact, circular, consistent with a point-like central energy source surrounded by a glowing cocoon. Exactly what the buried black hole model predicts. The other 30% transformed into something unrecognizable. In ultraviolet, these objects lost their sharp, circular shape entirely. They became fuzzy, extended, asymmetric blotches. Some looked like smears across the sky. Others had irregular edges or multiple brightness peaks. A few looked almost chaotic, with light distributed in patterns that had no obvious center and no clean structure. This was deeply unexpected. If all the dots were the same type of object viewed from different angles or at different stages of their evolution, the ultraviolet images should vary somewhat but stay recognizable. The transformation into completely different morphologies suggested that at least some of the dots were fundamentally different objects. Not buried black holes at all, but something else entirely that happened to produce similar infrared signatures. The fuzzy ones immediately generated competing explanations. The first possibility is that these are the little red dots caught mid-transition. As the cocoon begins to break apart, the gas does not disperse uniformly. It tears, forms gaps, and gets blown outward in irregular patterns. An object in that phase would look compact and circular in infrared, but chaotic in ultraviolet, because the scattered gas catches ultraviolet light differently than the tightly contained cocoon does. The second possibility is that some of the fuzzy objects are galaxy mergers. When two early galaxies collide and begin merging, the collision generates enormous amounts of light, including infrared, while the merger itself looks chaotic and extended at higher energies. From a distance of 13 billion light-years, a merger happening in the first billion years might appear compact in some wavelengths and sprawling in others. The third possibility is that a subset of the dots are massive dying stars, a class of stellar objects called supermassive stars that some theorists predict existed in the very early universe, stars hundreds of times larger than anything alive today, burning out in slow, luminous collapses that could mimic the signature of a buried black hole in certain wavelength ranges. What the ultraviolet test confirmed is that the little red dots are almost certainly not one thing. They are a population of objects that overlap in their infrared appearance but diverge dramatically when examined more closely. The buried black hole model explains the majority. The minority are still being argued over, and the fact that 30% remain unexplained means the early universe is still keeping some of its secrets. The fuzzy ultraviolet dots needed their own explanation. 3 candidates survived serious scrutiny. The first candidate is something that happens in the modern universe as well, but on a scale that was far more common in the early universe when galaxies were younger, smaller, and more tightly packed in a cosmos that had not yet expanded to its current size. Galaxy mergers. When two galaxies collide, which happens more frequently than the word collision implies, because galaxies are mostly empty space and they pass through each other rather than smashing like solid objects, the event still creates enormous disruption. Gravitational tides pull stars and gas into long streaming tails. The gas clouds in both galaxies compress against each other, triggering sudden bursts of star formation. The supermassive black holes at the centers of both galaxies eventually spiral together and merge. The whole process is chaotic, extended, and produces light in patterns that look nothing like a single compact object. In the early universe, the higher density of galaxies in a smaller cosmic volume made mergers far more frequent than they are today. A merger observed from 13 billion light-years away through 13 billion years of cosmic expansion could plausibly appear as a dim, compact red dot in infrared but resolve into a chaotic smear in ultraviolet. The second candidate is more exotic: supermassive stars. In the modern universe, the largest stars reach about 100 to 200 times the mass of our Sun. Above that threshold, stars become unstable. But theoretical models of the very early universe, when the gas was pure hydrogen and helium with no heavier elements to complicate the physics, predict that far more massive stars could have formed, objects reaching 10,000 or even 100,000 solar masses. These objects would not shine the way normal stars do. They would be bloated, unstable, incredibly bright, and short-lived. Their death would not be a standard supernova. They would collapse slowly and violently over thousands of years, a process called a supermassive star collapse. During that collapse, their light output could resemble a little red dot in certain wavelengths, while appearing extended and irregular in ultraviolet. Finding a supermassive star in the act of collapse would be one of the most significant discoveries in observational astronomy. It would confirm a category of object that has only ever existed in theoretical models. The third candidate connects back to the direct collapse black hole theory. During the formation of a direct collapse black hole, before the system reaches its stable feeding configuration, the infalling gas goes through a chaotic transitional phase. The light from this phase might look disordered and extended in ultraviolet, while still appearing point-like in infrared. All three explanations are live. None has been confirmed for the fuzzy subset. What this tells us is something important about science at the frontier. When you point the most powerful telescope ever built at the earliest observable era of the universe, you do not get clean answers. You get a population of objects that share some properties, diverge on others, and resist every attempt to collapse them into a single tidy category. The early universe was messier than any model predicted. 1,000 is a large number of anomalies. When a strange object appears once in an astronomical survey, it might be a glitch, a rare event, or an artifact of the observation process. When it appears 10 times, it is a confirmed phenomenon. When it appears over 1,000 times and keeps appearing in every new image taken, it is telling you something fundamental about the structure of the universe. The little red dots are everywhere in the early universe. They are not clustered in one region of the sky. They appear in every direction. Webb has pointed at deep space, scattered across the background of image after image, hiding behind foreground galaxies, sitting in the spaces between them, appearing in data taken for completely unrelated research goals. Teams studying early galaxy formation found them. Teams studying cosmic dust found them. Teams analyzing the intergalactic medium found them. Nobody was specifically looking for the dots at first, and yet they kept appearing. The sheer number changes how astronomers think about the early universe. Before Webb, the standard picture of the first billion years was relatively sparse. A few bright galaxies, some early quasars, the gradual assembly of cosmic structure from primordial gas. The early universe was thought to be mostly quiet, mostly dark, with only the most massive and energetic objects visible at all. The dots rewrite that picture completely. The early universe was crowded with compact, intense, rapidly feeding black holes. They were common. They were distributed throughout the observable volume of that era. Whatever process produced them was not rare or exceptional. It was routine, a standard feature of the universe in its first billion years. This raises a density question that nobody has fully answered yet. If over 1,000 dots are visible in the fraction of the sky that Webb has examined in detail, extrapolating across the full sky suggests there could be millions of these objects from the early universe that we have not yet catalogued. The ones Webb has found are almost certainly the brightest, the most extreme, the easiest to detect. The full population of early buried black holes might be far larger and far more significant than current numbers suggest. There is also a completeness problem. Webb has only been operating for a few years. It has surveyed a small fraction of the accessible sky in the kind of depth needed to detect the dots. Every new deep field image adds more. The catalogue is growing. A universe where supermassive black holes were forming everywhere in enormous numbers during the first billion years is a very different universe from the one textbooks described before 2022. It is a universe where the formation of massive black holes was a normal, widespread, almost industrial process, happening simultaneously across enormous distances. And if that is the case, the modern universe is built on a foundation that nobody fully understood until a gold-coated telescope stared at a grain of sand-sized patch of black sky and found it full of crimson dots. The numbers surrounding the little red dots keep producing results that should be impossible. The density paradox is the clearest example. It is the calculation that destroyed the star cluster theory early on, and returning to it now with a better understanding of what the dots actually are makes the numbers even more striking. The brightest little red dots shine with the equivalent of 250 billion suns. The measured size of the light-emitting region in the brightest examples is less than 3/10 of a light-year across. Let that sit for a second. 3/10 of a light-year is about 1.8 trillion miles. That sounds like a vast distance until you hold it next to the scale of actual galaxies. The Milky Way is 100,000 light-years across. The nearest galaxy to ours, the Andromeda Galaxy, is about 2.5 million light-years away. 3/10 of a light-year is a speck in that context, smaller than the distance between our Sun and its nearest stellar neighbor by a factor of more than 10. Now pack 250 billion suns worth of energy output into that speck. If that energy came from actual stars, the density of stars required would be so extreme that gravity would collapse the entire structure in moments. Stars that close to each other are not stable. They merge, explode, and rip each other apart through gravitational tidal forces. The cluster could not survive long enough to shine steadily, and the dots have clearly been shining for millions of years at minimum. The density of energy output from these objects has no parallel anywhere in the modern universe. The densest known star clusters, the most packed collections of stars ever confirmed, produce a tiny fraction of this energy from a comparable volume. To match the output of a little red dot using only stars, you would need a structure so compact and so massive that it would immediately collapse into a black hole anyway. The paradox loops back on itself. Stars cannot produce the energy. A black hole can. But a black hole of the required mass, actively feeding at the required rate, should be announcing itself with X-ray and radio emissions loud enough to detect from across the universe. The dots are not doing that. The resolution is the cocoon, as discussed before. But the density paradox is worth sitting with independently because it illustrates something about the physical extremity of these objects that no single statistic captures on its own. The little red dots are the most energy-dense environments that have ever been directly observed in the history of the universe. More dense in their output than any star cluster, more compact than any confirmed galaxy, louder than anything else in their era, but almost perfectly sealed from detection. They represent a configuration of matter and energy that the modern universe simply does not produce anymore. Whatever physical conditions allowed these structures to exist, those conditions are gone. The universe built something extraordinary in its first billion years, ran that process at industrial scale, and then stopped permanently. The word ionized gets used frequently in descriptions of the little red dots, but the mechanism deserves a direct explanation because it is the key to everything the cocoon accomplishes. An atom in its normal state is electrically neutral. It has a nucleus of protons and neutrons at the center, surrounded by a cloud of electrons. The number of electrons matches the number of protons, so the positive and negative charges cancel out. Neutral atoms interact with light in specific ways, absorbing and emitting photons only at particular wavelengths determined by their atomic structure. When intense energy hits a neutral atom, specifically photons with enough energy, or extreme heat, or both, the atom can lose one or more of its electrons entirely. Without the electrons to balance the nuclear charge, the atom becomes positively charged. This charged atom is called an ion. The gas it forms is called ionized gas, or plasma, which is the fourth state of matter alongside solid, liquid, and gas. Ionized gas behaves completely differently from neutral gas. Neutral gas is relatively transparent to many forms of radiation. Light can pass through it, scatter off it, but often travels reasonably well. Ionized gas, by contrast, is extraordinarily opaque to high-energy radiation. The free electrons that were stripped from atoms now float loose in the gas, and free electrons are extremely efficient at absorbing and scattering photons. X-rays and ultraviolet radiation, the wavelengths that a feeding black hole produces in enormous quantities, are absorbed rapidly when they encounter a thick enough layer of ionized gas. The cocoon surrounding the little red dots is so dense with ionized gas that X-rays generated near the black hole travel only a short distance before being absorbed by a free electron. The electron picks up the energy and re-emits it at a lower frequency, usually in the infrared. The energy does not disappear. It gets converted from high-energy X-ray to lower-energy infrared, which is what escapes the cocoon, and what Webb detects as the red glow. The cocoon is not blocking energy, it is converting it. The most violent radiation produced by a feeding supermassive black hole is being transformed, wavelength by wavelength, into the soft red glow of heated gas. This conversion process also helps explain how the cocoon sustains itself. The absorbed X-ray energy heats the gas continuously. Hot gas expands. Expanding gas maintains pressure. The thermal pressure of the heated cocoon pushes outward, while gravity and radiation pressure from the black hole push inward. The system reaches a balance that can persist for millions of years. The cocoon is simultaneously the product of the black hole's feeding and the shield that hides it. The black hole creates the ionized environment that then conceals it. It is a near-perfect self-perpetuating disguise that nature assembled without any intent, purely from the physics of how matter and energy interact at extreme densities. Understanding this mechanism was one of the central achievements of 4 years of post-discovery research. It transformed the little red dots from a genuine mystery into something explainable, even if not yet fully understood in every detail. No single telescope cracked the mystery of the little red dots. The breakthrough came from combining two instruments that were never originally designed to work together on the same problem, observing the same patch of sky at the same time in completely different wavelength ranges. Webb sees infrared. Chandra sees X-rays. They are physically located in different orbits. Webb sits about 1 million miles from Earth at a gravitationally stable point called the second Lagrange point, kept cold by its sun shield. Chandra orbits Earth in a highly elliptical path, swinging out to about 85,000 miles at its farthest point. Getting them to look at the same object simultaneously requires careful coordination between two different mission operations teams. It also requires knowing roughly where to look, which 4 years of Webb observations had finally made possible. When the coordinated observation data came back in April 2026, researchers went through it object by object. Most of the little red dots showed up exactly as expected in Webb's infrared data. Bright, compact, red. In Chandra's X-ray data, most of them were silent, consistent with the cocoon model. One was not. The object sat 11,800,000,000 light-years away. In Webb's data, it looked like every other dot. In Chandra's data, it showed a faint but statistically significant X-ray signal. Not strong, not loud, but present. Unmistakable when the noise was properly accounted for. The X-ray signal had specific characteristics that told astronomers more than just its existence. Its energy level and its weakness, relative to the infrared output, pointed to a partially obscured source. The X-rays were not escaping freely. They were leaking through gaps in the cocoon, reduced and filtered, but detectable. The Chandra data was seeing the black hole through the cracks in its own disguise. This single detection validated the entire buried black hole model in a way that 4 years of indirect evidence had not quite achieved. Indirect evidence argues from consistency. The model predicts this, and the observations match, so the model is probably right. Direct detection argues from observation. The X-rays are there, and X-rays at this energy level from this type of object come from one source only. The confirmation also suggested a timeline. The X-ray detection pointed to a dot in a specific phase of its evolution, past the fully sealed cocoon stage, not yet fully open, in the middle of the transition where the shell was thinning and cracking. This implied that other dots in the catalogue were at different phases. Some with intact cocoons, completely silent, some like this one, just beginning to leak, and presumably some that had fully cleared their cocoons and become standard visible quasars. The little red dots, the transition object, and the quasars of the modern and Middle Age universe might all be the same thing viewed at different points in a single long life. 2 telescopes pointed at the same patch of ancient sky finally made that story possible to tell. Every large galaxy in the known universe has a supermassive black hole at its center. Every single one that has been examined closely enough. The Milky Way has one called Sagittarius A star, with a mass of about 4 million solar masses. Andromeda has one estimated at over 100 million solar masses. The galaxy, Messier 87, famous for producing the first ever direct image of a black hole's shadow, has one weighing 6.5 billion solar masses. These black holes are old. They formed long ago and have been sitting at the centers of their galaxies ever since. Tracking their origins is one of the deepest questions in astrophysics. Where did they come from? And what did they look like when they were young? The little red dots offer a possible answer. If the sequence holds, if the dots are young, feeding black holes that eventually clear their cocoons and become visible quasars, and if those quasars then slow their feeding as their gas supply is exhausted and settle into the relatively quiet state of modern galactic center, black holes, then the dots might be the literal ancestors of the black holes we see today. The math can be checked roughly. The number of supermassive black holes in the modern universe, combined with their average masses, gives a total mass in black holes that needs to have been assembled somewhere in the past. The number of little red dots, their estimated masses, and their density across the early universe gives a total available mass. The numbers are in rough agreement. There are enough dots, massive enough, to be the seeds of the modern black hole population. This is not a proof. The connection is plausible and supported by the rough numbers, but confirming it requires tracing the evolutionary path in detail, which requires more observations across more cosmic time than Webb has yet provided. But the idea has a striking implication. The black hole at the center of the Milky Way, Sagittarius A star, which sits about 26,000 light-years from Earth and has been there since our galaxy formed, may have once been a little red dot buried in its cocoon, feeding furiously on primordial gas, invisible to any instrument that could have existed at the time. If you could go back 13 billion years and look at the location where the Milky Way's center would eventually form, You might see a tiny red point of light hiding in the background of the early universe, indistinguishable from the thousand others scattered across the sky. And from that point, over billions of years of feeding and merging and gradual starvation, it grew into the 4 million solar mass sleeping giant, sitting at the heart of our galaxy today. The dots are not just an early universe curiosity, they might be the origin story of every galaxy that ever formed. The ancestor theory is compelling. It is also incomplete, because there is another possibility that astronomers have not ruled out, and it is less satisfying but potentially just as important. Some of the little red dots may not have grown into anything. In the history of the universe, not every process leads somewhere. Some evolutionary paths produce objects that thrive and persist. Others produce objects that flourish briefly under specific conditions and then simply stop when those conditions change. The little red dots existed in the first billion years, and they appeared to be exclusive to that era. The modern universe does not contain objects that match their profile closely. That absence is explained by the ancestor theory as evolution. The dots grew up and became quasars and then quiet galactic black holes. But it could also be explained by extinction. A dead-end path would look like this. The little red dots form in the early universe through direct collapse, feed rapidly on primordial gas streams, grow to millions of solar masses, and then run out of fuel. The cosmic filaments that fed them thin out as the universe expands. The gas supply drops. The black hole, unable to sustain its feeding rate, begins to starve. Without the continuous inflow of gas, the accretion disk fades. The radiation drops. The cocoon, no longer heated from the inside, cools and disperses without the dramatic blowout that creates a visible quasar phase. The black hole becomes dormant. It sits at the center of whatever structure it built around itself, dark and quiet, not massive enough to have grown into a modern giant, not active enough to be detectable. It fades from the observable universe. Under this model, some portion of the little red dots, perhaps the less massive ones, perhaps those that formed in environments where the gas supply was more limited, did not become the ancestors of modern supermassive black holes. They became intermediate mass black holes, objects in the range of 10,000 to 1 million solar masses, sitting dormant in galaxies throughout the universe. Intermediate mass black holes are one of the most sought-after and least confirmed categories in astrophysics. Stellar black holes, up to a few hundred solar masses, are confirmed. Supermassive black holes, millions to billions of solar masses, are confirmed. The gap between them, the intermediate range, is almost empty in the confirmed observation record. If a significant fraction of the little red dots evolved into dormant intermediate mass black holes, they could be filling that gap right now, invisible and undetected, scattered throughout the modern universe in the centers of smaller galaxies. Finding one would be one of the most significant observational achievements in decades. The dead-end path does not contradict the ancestor theory. Both could be true simultaneously, applying to different subsets of the little red dot population, depending on their initial mass, their gas supply, and the specific conditions of their local environment. The early universe may have produced two separate legacies from the same starting point, giants that grew and still rule, and ghosts that stalled and disappeared into silence. Physics is not a fixed set of truths handed down once and kept forever. It is a set of models that describe what we have observed, refined continuously as observations improve. When observations start producing results that the current models cannot accommodate, the models change. This has happened before. It will happen again. The little red dots may be forcing the next major revision. The specific rule under pressure is the one governing how black holes grow. The current framework, built on decades of observations of black holes in the modern and Middle Age universe, describes a process that is orderly, limited, and predictable. Seeds form from dying stars. Feeding is capped by radiation pressure at the Eddington limit. Growth is slow enough that the most massive black holes in the universe today make sense as the product of billions of years of accumulated eating and merging. That framework produced accurate predictions for every black hole observation made before 2022. The little red dots are outside its range. The masses are too high for the available time. The feeding rates implied by the energy output appear to exceed standard limits. The formation mechanism, if direct collapse is correct, has no confirmed modern analog. The cocoon behavior, absorbing radiation without being dispersed by it, does not match how gas behaves around feeding black holes in the modern universe. Every one of these discrepancies is a point where the current rules fall short. Each one is a place where either the observations are wrong, which careful analysis has made increasingly unlikely, or the rules need updating. Updating the rules does not mean throwing out everything known about black hole physics. It means identifying which assumptions were too narrow, which were based on conditions specific to the modern universe that did not apply in the early universe, and extending the framework to cover the full range of what black holes can do across cosmic time. One specific update that many researchers now consider likely is a revision to the effective Eddington limit in dense early universe environments. The standard limit is derived for conditions that apply in modern accretion disks. In the thicker, more chaotic accretion flows implied by the little red dot cocoons. The limit may be higher. Gas flowing in from multiple directions in a thick disk allows more mass to reach the black hole before radiation pressure can reverse the flow. If this super Eddington regime is real and common in the early universe, the growth rate problem becomes less severe. Another likely update is to include direct collapse as a standard formation channel alongside stellar collapse. If the early universe routinely produced massive black hole seeds through direct collapse, then the growth problem does not start from stellar masses at all. It starts from something much larger, and the timeline pressure relaxes significantly. Neither update requires abandoning the known laws of physics. Both sit within the theoretical framework that already exists. They require expanding that framework, applying it more broadly, and accepting that the universe in its youth operated in ways that the modern universe no longer does. That kind of expansion has happened before. It will keep happening as long as telescopes keep finding things that should not exist. The center of the Milky Way is 26,000 light-years away. That is close enough that astronomers have studied it in detail, tracking individual stars orbiting the central black hole called Sagittarius A star, and measuring their speeds and paths with enough precision to confirm the black hole's mass at about 4 million solar masses. It is the best-studied supermassive black hole in the universe, simply because it is the nearest one. Sagittarius A star is quiet today. It occasionally flares, consuming small amounts of gas or dust that wander too close, but it is not actively feeding at any dramatic rate. It is a sleeping giant sitting at the center of a galaxy that has been building around it for roughly 13 billion years. Where did it come from? One possibility is that it started as a stellar black hole, the remnant of a massive star that died in the very early Milky Way, and grew slowly over billions of years through a series of mergers and feeding episodes. This is the standard model answer. The other possibility, which the little red dots have made considerably more interesting, is that Sagittarius A star began as a direct collapse black hole in the first billion years of the universe, wrapped in a dense gas cocoon, blazing with the energy of a billion stars, invisible to any hypothetical observer of that era. If this is correct, there was a moment, about 13 billion years ago, when the object that would become our galaxy's central black hole looked exactly like a little red dot, feeding furiously, growing rapidly, sealed inside an ionized cocoon that hid it from the universe, a tiny crimson point in the background of the early cosmos, indistinguishable from the 1,000 others surrounding it. Over the following billions of years, the cocoon cracked. The dot became a quasar, blazing briefly before its gas supply dwindled. The quasar faded into a quieter state as the galaxy formed around it, stars gathering into the spiral arms that would eventually produce our sun and our planet. Merger after merger added mass and structure. The black hole at the center grew in fits and starts, dormant for long periods, briefly active when a fresh supply of gas fell inward. And now it sits there, 4 million times the mass of our Sun, doing very little, while we orbit it once every 230 million years without giving it much thought. There is something striking about standing on a planet, looking up at a galaxy, and knowing that the center of that galaxy might have once been the same type of object that astronomers are puzzling over right now in the distant early universe. The little red dots are not just a feature of some ancient and unreachable era. If the ancestor theory is right, one of them became the object that anchors the structure of our entire home galaxy. The mystery that Webb uncovered is not remote from us. It may be the story of where we came from. The 1,000 little red dots in the current catalogue are almost certainly not all of them. Webb has surveyed only a fraction of the sky in the depth required to detect these objects. The dots in the current catalogue represent the brightest end of the population, the most extreme, the easiest to pick out against the background noise of the early universe. Fainter dots, lower mass dots, dots at slightly different stages of their evolution, are likely present in enormous numbers, but have not yet been individually catalogued. Astronomers use a statistical technique called luminosity function analysis to estimate the true size of a population from the detected sample. You count how many objects you find at each brightness level, fit a mathematical curve to that distribution, and extrapolate to the fainter end where your observations become incomplete. When this analysis is applied to the little red dots, the numbers are striking. The full population of early universe buried black holes, including those too faint for current Webb observations to confirm individually, is estimated to be in the millions across the observable sky. Some estimates push higher. This means the early universe was not just somewhat busy with black hole formation, it was saturated with it. Black holes of millions of solar masses were forming simultaneously across the entire observable universe in the first billion years, distributed through the cosmic web of filaments and density peaks, so numerous that looking at any sufficiently deep patch of early universe sky almost guarantees finding several. If those estimates are accurate, the first billion years of the universe produced more supermassive black hole mass than all the star formation and merger activity in the following 12 billion years combined. The early universe was the peak production era for massive black holes, and we had no idea until Webb made the dots visible. Each new deep field image Webb captures adds more candidates to the list. The rate of discovery has not slowed. Researchers processing Webb data continue to find new dots in archival images taken for other purposes. The catalogue is still growing, and the total number it will eventually reach is unknown. There is also the question of what else is hiding at similar redshifts in wavelength ranges or at brightness levels that even Webb struggles with. The little red dots revealed themselves because they were bright and numerous enough to show up in routine deep field imaging. Objects that are fainter, smaller, less numerous, or emitting primarily in wavelength ranges Webb does not cover optimally might still be out there, waiting for the next instrument. The early universe has been delivering surprises continuously since Webb turned on. The rate of surprises has not decreased. The James Webb Space Telescope will not operate forever. It carries a finite fuel supply for maintaining its position and orientation. Estimates place its operational lifetime at somewhere between 15 and 20 years from its launch in 2021. After that, it will drift and eventually become unusable. Every year of Webb observations is valuable, and teams around the world compete intensely for observing time on the instrument. The next phase of little red dot research will push Webb to its limits. Coordinated observations with Chandra will continue, hunting for more X-ray detections among the dot population to confirm the buried black hole model across a broader sample. Researchers want to find dozens of X-ray emitting dots, not just one, to map the transition phase across a range of masses and cosmic ages. Webb observations at multiple wavelengths will try to resolve the ultraviolet mystery, pinning down whether the fuzzy 30% are mergers, supermassive stars, or something else. Detailed spectroscopy, the analysis of how the light breaks down into its component wavelengths, can reveal the chemical composition of the cocoon gas, which would provide clues about the environment of formation. But Webb has limits. It cannot resolve the internal structure of the dots in detail. It cannot directly image the accretion disk or the central black hole. It can only read the light that escapes the cocoon and infer what is happening inside. The next generation of observatories will go further. The extremely large telescope currently under construction in Chile will have a mirror almost 130 feet across, 6 times the light collecting area of any existing ground-based telescope, and will be capable of spectroscopy on early universe objects with a precision that Webb cannot match. It will not see the infrared from the ground as well as Webb does from space, but for certain wavelength ranges and certain types of measurement, it will exceed Webb significantly. Proposed future space telescopes, including designs that extend into far infrared and sub-millimeter wavelengths, would be able to probe the cocoon itself, mapping its density and temperature structure in ways that current instruments cannot. If built, these observatories would turn the little red dots from inferred objects into directly characterized ones, and X-ray astronomy is due for a major upgrade. Next-generation X-ray observatories with far greater sensitivity than Chandra could detect the faint X-ray leakage from transition phase dots across a much larger sample, mapping the full population of cracking cocoons across the first billion years. The tools to finish this story are coming. Some are already being built. The little red dots are not an isolated discovery. They sit inside a larger revolution in how astronomers understand the structure of the early universe. A revolution that Webb has been driving since its first images arrived in 2022. The dots are one of the most dramatic examples, but the broader picture they point to is even more significant. Before Webb, the standard model of cosmic structure predicted a relatively gradual build-up of mass in the early universe. Small galaxies forming first, then slowly growing through mergers into the large galaxies of today. Black holes growing alongside their host galaxies in a co-evolutionary relationship where each regulated the other. The whole process paced and orderly, matching the predictions of simulations built on known physics. Webb has found galaxies that are too massive, too structured, and too evolved to exist in the timeline the standard model predicts. It has found black holes that are too large for their age. It has found the little red dots, a whole population of objects that were not in any model at all. The early universe appears to have assembled itself faster than the standard model says was possible. Structure formed earlier. Black holes formed earlier and grew faster. Galaxies organized earlier. The first billion years was not a slow prologue to the real story of the universe. It was itself an intense, rapid, densely active period that produced conditions and objects the middle and modern universe cannot replicate. This suggests that something about the standard cosmological model, the equations and assumptions that describe how the universe evolves from the Big Bang forward, is either incomplete or wrong in ways that only become visible at early cosmic times. The model works very well for the last 10 billion years. The first 3 billion years, and especially the first 1 billion, keep producing results the model did not predict. The little red dots are the sharpest example of this gap. They are objects the model said should not exist in the numbers or at the masses Webb is finding. Their existence does not disprove the model, but it strongly suggests the model needs expanding with new physics or new processes that apply specifically to the conditions of the very early universe. Finding those new processes is now one of the central goals of observational cosmology. Every dot Webb finds and characterizes is another data point constraining what those processes could be. Every spectral measurement, every mass estimate, every X-ray detection is a piece of evidence that future theorists will use to build the revised picture of how the universe really assembled itself. The dots are not just an answer, they are a question mark written in the oldest light in the universe. Finding the answer to what the little red dots are took 4 years. The answer immediately produced a harder question. If the early universe was full of supermassive black holes forming through direct collapse, feeding on cosmic filaments, growing to millions of solar masses in less than 1 billion years, then the process that created them had to already be in place when the universe was very young. Direct collapse requires specific conditions: massive gas clouds, ultraviolet radiation from nearby early stars, and gravitational density peaks dense enough to prevent fragmentation. The ultraviolet radiation that enables direct collapse has to come from somewhere. It comes from the first generation of stars, called population 3 stars, which formed before any heavy elements existed. These stars burned hot and fast and produced the ultraviolet environment that allowed direct collapse to happen in their vicinity. So the little red dots may depend on population 3, stars existing first. Population 3 stars have never been directly observed. They are predicted by theory, expected to have existed in the first few 100 million years of the universe, and assumed to have ended in supernovas that seeded the universe with the first heavy elements. But no telescope has ever confirmed one. If Webb finds evidence of population 3 stars, or their remnants, it would fill in the step before the dots in the chain of cosmic history. It would tell us how the conditions for direct collapse were assembled. But that pushes the harder question back one more step. What came before population 3 stars? The very first stars required the first gas clouds to collapse, which required density fluctuations in the early universe to have been in the right configuration, which traces back to the physics of the first few minutes after the Big Bang, when the universe was hot enough that particles were still being created and destroyed from pure energy. Every answer in cosmology is this way. Every explanation for what something is requires an explanation for what made it possible, which requires an explanation for what made that possible. The chain extends backward through time until it reaches the beginning of the universe itself, and there the chain runs out. The Big Bang produced a universe with specific properties, specific densities, specific temperature distributions, specific patterns of tiny quantum fluctuations that eventually grew into every structure that exists today. Those starting conditions were set at a moment when physics, as currently understood, breaks down completely. The mathematical tools of general relativity and quantum mechanics, which together describe everything else in the universe with extraordinary precision, fail at the exact instant of the Big Bang. The little red dots, in their strange and surprising way, are a thread that pulls all the way back to that fundamental unknown. Following them far enough leads to the edge of what physics can currently say about the universe. And past that edge, there is only the question. Stand outside on a clear night, far from city lights. Look up. Every star you can see is inside the Milky Way, within a few thousand light years of Earth. The fuzzy patch of the Milky Way stretching across the sky is the combined light of hundreds of billions of stars in our own galaxy. Beyond that, invisible to the naked eye but detectable with instruments, are billions of other galaxies stretching to the edge of the observable universe. All of that structure, every star, every galaxy, every black hole, every planet, came from the same starting point. A universe about the size of a marble, impossibly hot and dense, that expanded rapidly in the first fractions of a second after the Big Bang and has been expanding ever since. Everything that exists today was contained in that marble. The little red dots are a clue about what happened in the very first chapter of the story that followed that beginning. In the first second, atomic nuclei formed. In the first few 100,000 years, atoms formed, and the universe became transparent to light for the first time. In the first few 100 million years, the first stars ignited. And then, in the first billion years, something happened that nobody predicted. Black holes formed, enormous ones. Immediately, wrapped in cocoons of ionized gas, buried and silent, blazing with the energy of hundreds of billions of suns from spaces smaller than our solar system, thousands of them. possibly millions across the full sky, distributed through the young cosmic web like seeds, or like anchors around which the modern universe would eventually organize itself. The question of why the early universe produced these objects so quickly, so abundantly, and in such an extreme form is not fully answered. The buried black hole model explains what they are. The direct collapse theory explains one possible path to their formation. The cosmic filament model explains how they fed so fast. The transition sequence explains how they evolved into the quasars and sleeping giants of the modern universe. But why the universe had the exact starting conditions that made all of this possible, why the quantum fluctuations from the Big Bang produced precisely the density peaks that allowed direct collapse, why the first stars formed in exactly the right places to create the ultraviolet environment that enabled the dots. These questions trace back to the beginning itself, where current physics goes quiet. The little red dots are, in the most literal sense, a message from the edge of time. Their light left them over 13 billion years ago, before Earth existed, before the Sun existed, before the Milky Way had fully formed. That light traveled across an expanding universe, stretched by the expansion from visible to infrared, passed through billions of years of cosmic history, and arrived at a golden mirrored telescope floating cold and silent a million miles from a small planet. We decoded the message, and the message says, "The beginning was stranger than anyone imagined. What comes before the beginning is the only question left, and we are only just learning how to ask it."